Hello, my name is Ben Shappee. I'm a graduate student here at The Ohio State University. I'm currently working with Kochanek and Stanek, and I'm here to discuss our recent paper entitled Type 1a Single Degenerate Survivors Must Be Overluminous. Type 1a supernovae are among the most luminous explosive events known, and are observable from halfway across the universe. Also, their peak luminosity is well correlated with how quickly they fade, allowing astronomers to use Type 1a supernovae to measure distances throughout our universe. Efforts by two teams to discover and follow up Type 1a supernovae led to the discovery of the accelerating universe, which was awarded the Nobel Prize for Physics last year. However, even though Type 1a supernovae have been crucial in shaping our understanding of the universe, the exact nature of their progenitor systems remains theoretically ambiguous and observationally elusive. While it is commonly accepted that Type 1a supernovae result from the thermonuclear explosion of a carbon-oxygen white dwarf in a close binary system, the nature of the binary companion and the chain of events leading to this supernova explosion are still uncertain. A popular model for the progenitor system, illustrated here, has a carbon-oxygen white dwarf accreting material from a solar-like main sequence star until the white dwarf reaches a critical mass, when it then explodes as a Type 1a supernovae. The supernova ejecta will then impact the companion, which is illustrated in this cartoon. While many aspects of the interaction of the explosion with the donor have received much attention, it has not been fully appreciated that the properties of the donor star also undergo drastic changes immediately following the explosion. Primarily, this impact sends a shockwave into the companion, which leaves the star's envelope hot and extended and removes approximately 15% of the mass. It was recently shown that the star loses mass mainly because of ablation or heating and not momentum transfer, so the two cannot be treated as independent variables. In this paper, we modeled the future evolution of the companion star with a stellar evolution called MESA. To match hydrodynamic simulations, the companion star must be heated by approximately 4 times 10 to the 47 ergs, and it commences its post-explosion evolution with its radius and luminosity greatly increased. In this modified version of our figure 1, we show the luminosity evolution of the companion. For the first couple years after the supernova, the companion will be a few hundred solar luminosities. It will then fade to between 10 and 20 solar luminosities after 1,000 years, and it will remain significantly overluminous for approximately 10,000 years. This means that leftover stars in Type 1a supernova remnants should still be approximately 20 times more luminous than they were before the explosion. This greatly strengthens the arguments against a single degenerate scenario for the LMC supernova remnant 0609-67 and essentially rules out Tycho star G as a survivor of supernova 1572. Finally, such luminous donors should be observable with the Hubble Space Telescope within 10 megaparsecs, where there are a number of recent Type 1a supernovae. In figure 5 of our paper, we show the current B, V, R, and I light curves of the recent supernova in M101 2011 FE. Using the current decline rate, we extrapolate these light curves and show the results in dotted lines. We then show the expected luminosity of the companion star in each band in dashed lines. So, where the dashed and dotted lines cross, the companion will be as luminous as the rapidly fading supernova remnant. This occurs between 2 and 3 years after the explosion, at which point there should be a break in the R and I light curves as the companion begins to dominate the light. The lack of such a break would provide strong evidence against the existence of a main sequence companion. If you'd like to know more about our work, please see our paper which is posted in the archive. Thank you.